All right, welcome everyone. If you're studying cybersecurity, grinding for that CCNA, or just trying to wrap your head around networking for an exam, you are exactly where you need to be. Today, I'm going to be your dedicated professor, and we're diving into this explainer to master the literal foundation of the internet, Layer 1. So grab your notebooks, get comfortable, and let's jump right in. So here's a question for you. Why do we even need the OSI model just to send a simple WhatsApp message? I mean, it's just text, right? Well, not quite. When you hit send on a hello, that message doesn't just magically teleport through the air to your friend's phone. No way. To make that trip, your tiny little hello has to be chopped into smaller pieces, addressed, checked for errors, converted into raw electrical or radio signals, and then perfectly stitched back together on the other side. That whole crazy step-by-step assembly line, yeah, that's exactly what the OSI layers handle.
Okay, here's our game plan for today's explainer. We'll start with an OSI model overview. Then we'll be decoding the physical layer, looking at transmission media explained, going over devices and topologies, and finally we'll wrap up with physical network problems. Let's get to it.
All right, Section 1, the OSI model overview. Because, to understand the foundation, we really need to see the whole building first.
The journey our data takes is this really fascinating process called encapsulation. Think of it like a set of Russian nesting dolls. When you send data from the application layer, it starts out as just plain data. But as it travels down the OSI stack, it morphs. At the transport layer, it becomes a segment. Down at the network layer, boom, it's wrapped up into a packet with IP addresses. Hit the data link layer, and now it's a frame with MAC addresses. And finally, by the time it hits the physical layer, it's stripped all the way down to raw bits, just pure zeros and ones. It's literally like putting a letter in an envelope, then a box, and then tossing it into a massive shipping container. Now, if you want a bulletproof way to memorize the full 7-layer stack for your exams, and trust me, your teacher will ask this, write down this classic mnemonic. All people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. While the upper layers handle all the fancy user services and software today we're living at the absolute bottom of the barrel, Layer 1. Which brings us to Section 2, decoding the physical layer. Let's zoom in right where the digital world smashes into the physical world. So, what actually is it? The physical layer, or Layer 1, is the absolute lowest OSI layer. Its one and only job is transmitting raw bits, those zeros and ones, over a physical medium. And it does this using electrical, optical, or radio signals. Think of it like this. Layer 1 is just the road. It doesn't care if a Ferrari or a garbage truck is driving on it. It doesn't know what an IP address or a data frame even is. It's just there to provide the physical pavement for those bits to travel on.
Okay, pay attention here because this is a classic trap question on almost every networking exam. You need to know the difference between bandwidth, throughput, and latency. Bandwidth is the theoretical maximum capacity of your medium, basically how wide the pipe is. Throughput, though, that's the actual speed of data transfer you get in the real world, which, let's be honest, is always lower because of network overhead. And latency, that's your delay. Literally the time it takes for a single bit to travel from the sender to the receiver. You absolutely have to nail these concepts. Knowing the difference between what a cable should do and what it actually does is crucial.
All right, moving on to Section 3, transmission media explained. We know what the bits are, but what are the actual physical roads we use to send them?
Before we start looking at cables, we've got to answer a pretty fundamental question. How do our bits actually travel from point A to point B? I mean, a dumb copper wire has no clue what a 1 or 0 is, right? Well, this is where a little magic trick called encoding comes in. Encoding is the process where our digital zeros and ones are translated into real physical phenomena. If we're using a copper cable, a 1 might be a high voltage spike and a 0 a low voltage drop. In a fiber optic cable, it's actual pulses of light. And for wireless, it's all about tiny variations in radio waves.
Now, when we compare cables, you've probably heard of UTP, unshielded twisted pair. That's almost certainly what you've got plugged into your router at home. It's cheap. It gets the job done. But then you have STP, shielded twisted pair, which wraps the wires in an extra layer of metallic foil. And here is a guaranteed exam question for you. Why on earth are those internal wires twisted together in the first place? Well, they're twisted specifically to cancel out electromagnetic interference from the outside world and to stop crosstalk, which is basically signal bleeding from neighboring wires inside the cable itself. Pretty genius, right?
Take a look at the speed differences here. Standard Cat5e copper tops out around 1 gigabit per second, while Cat6 can push up to 10 gigabits. But then there's fiber optic. Fiber is the undisputed king of the physical layer. Because it uses literal light instead of electrical signals, it's completely immune to electrical interference. Plus, it is insanely fast and can span massive, massive distances without the signal degrading. Bottom line, if you need serious speed and distance, you ditch the copper and go straight to fiber.
But hey, what if we don't want to mess with cables at all? That brings us to unguided media. Wireless transmission still operates all the way down at layer 1, but it uses radio waves. When you connect to Wi-Fi at a coffee shop, you're using the IEEE 802.11 standard. That's literally a layer 1 physical standard for encoding bits into radio frequencies. Bluetooth is the exact same concept, just for much shorter distances. So even when there's zero physical wire, you're still relying on a physical layer medium. It just happens to be the air and electromagnetic waves.
Okay, section 4, devices and topologies. We've got our media, now let's look at the actual hardware living at layer 1 and how we physically arrange it. I want you to put your network admin hat on for a second. Imagine you're facing a massive outage. Here's your troubleshooting scenario. What happens if our physical topology completely fails? Well, the way you physically string your cables together, your topology, entirely dictates how resilient your network is when disaster strikes. Let's break down the main topologies because your professors love testing this. In an old-school bus topology, every device shares one single backbone cable. If that one cable snaps, boom, the entire network goes dark. It's incredibly vulnerable. That's exactly why modern networks rely heavily on the star topology, where everything connects to a central device. In a star, if a cable gets snipped, only that one specific computer drops off. Everyone else keeps working just fine. We also have ring topologies, which are circular, and mesh topologies. Mesh is the holy grail of redundancy because every device connects to multiple others. If a link dies in a mesh network, the data just casually takes a detour down another physical path. All right, let's talk about the hardware that actually lives at layer 1. Hubs and repeaters. Now, a repeater is super simple but incredibly useful. It just grabs a weakened, dying signal, gives it a boost, and regenerates it so it can travel further down the line. A hub, on the other hand, well, it's basically a multi-port repeater, but honestly, it's a very dumb device. Because it operates purely at the bit level, a hub has absolutely no idea what a MAC address is. If data comes into one port, the hub just blindly screams it out of every single other port. It's super inefficient and causes a ton of data collisions. And that, my friends, is exactly why modern networks use switches, which are smarter and live up at layer 2, instead of these ancient layer 1 hubs.
Okay, section 5, physical network problems. We've built the network. Now let's figure out how to troubleshoot it when things inevitably break in the real world.
Here's a super practical scenario for you. You're running a long copper cable all the way across a massive warehouse. What happens when that electrical signal naturally weakens over that long distance? Well, the bits start degrading, your ones start looking a whole lot like zeros, and the network connection totally drops. So how do you fix it? Well, here is your ultimate cheat sheet for physical network problems. Seriously, you might want to screenshot this one. Remember that signal weakening over distance? That's called attenuation. Your layer 1 fix, you slap a repeater halfway down the line to regenerate the signal. Okay, what if signals from different cables are leaking and mixing together? That's crosstalk. The physical solution there is making sure you use properly twisted pair cables. And what if you've got heavy factory machinery causing random electrical noise? That's EMI, or electromagnetic interference. The fix? You upgrade from unshielded UTP to shielded STP cables. Being able to look at a real-world issue and immediately link it to its physical layer solution, that is the mark of a true networking pro. So what's the big takeaway from our explainer today? It's this. Layer 1 is the ultimate foundation. No bits, no network, no internet, period. You could have the most beautifully configured routers in the world, flawless DNS settings up at the application layer, and perfectly secure TCP transport layers. But if a rat chews through your physical Ethernet cable or your Wi-Fi signal gets blocked by a giant concrete wall, literally none of it works. If the physical layer can't successfully transmit those raw bits, the upper 6 layers of the OSI model are completely useless. Which leaves us with this final, crucial thought. If layer 1 fails, none of the other 6 layers matter. Whenever you face a network outage, whether it's a tricky question on an exam or a real-life crisis on the job, always check your physical cables, check your blinking lights, and check your connections first before you dive into some crazy software troubleshooting rabbit hole. So ask yourself, is your physical foundation truly secure?
Thanks for hanging out with me on this deep dive into the OSI model. Keep studying hard, keep asking great questions, and I'll catch you in the next explainer.